Good morning. Today, I want to give lecture on reaction turbine. Myself, Satyaveer Singh, Assistant Professor, Department of Mechanical Engineering, IIMT College of Engineering, at Noida. So, the lecture topic is reaction turbine. Basically, what is reaction turbine? We will talk about that and what is the basic requirement of this turbine. Reaction turbine is basically, in case of reaction turbine, water at the inlet of the turbine possesses kinetic energy as well as the pressure energy. As water flows through the runner, a part of the pressure energy. And we can say that this uh, type of turbine is basically deals as that as water flows through the runner, a part of the pressure energy goes on changing into the kinetic energy. Thus, the water through the runner is under pressure and runner is completely enclosed in an airtight casing. So, casing and the runner are always full of water in case of the reaction turbine. Now, come to the next slide. In this slide, we can say that basically this is the giant hydro power plant in which these are the blades of the turbines, and this is basically the shaft. So, this is the actual view of the large hydroelectric power plant. So, we can say that if we discuss about the types of the turbines, so different types of reaction turbines are there. So we can say that different types of turbines are number one is inward flow radial reaction turbine, second is outer outward flow radial reaction turbine, and third is mixed flow turbine, and fourth is axial flow turbine. So we will discuss one by one. In case of inward radial flow reaction turbine, water flows from outward to inward, but in case of outward radial flow reaction turbine, water flows from inward to outward. So the mixed flow turbines, in case of mixed flow turbine, water flow radially but leave axially. So that is example of friction. That is Francis turbine is the example of the mixed flow. If we talk about the axial flow turbine, then water enters and leaves axially. Examples are Kaplan turbines and propeller turbines. These are two axial flow turbines. It can, in case of the Kaplan turbines is concerned, then runner blades are adjustable. So Kaplan turbine, the reaction blades, that is runner blades are adjustable, but in case of propeller turbine, runner blades are fixed types. Okay. Now we can say that uh, next is the what is the classification of the Francis turbines in more detailed way. Number one is the mixed flow turbine. In case of mixed flow turbine, water enters radially and leaves axially to the direction of rotation of the shaft. But reaction turbines basically at the interior of the turbine, both kinetic energy as well as the pressure energy are available, and it is of medium head and the medium flow rates. And this is the actual view of the basically reaction that is mixed flow turbines. Now, if we talk about the components parts of this type of turbine, basically this is the basic view of this turbine, and a number of parts are there. That is penstock pipe, spiral casing, guide vanes, governor mechanism, runner, and draft tube. So this is basically the excel exact figure, and this is called the main shaft, and this is the regulating rod, this is the guide vane mechanism, this is the runner blades, and then this is the draft tube, this last is the tail race, and this is the scrod casing. So this is the exact picture of the reaction turbine. Now come to next, that is the working principles of this turbine. Basically, there are number of parts of this turbines. First one is penstock. What is the function of penstock? A penstock is a large diameter conduit which carries water from dam or reservoir to the turbine house. Since Francis turbine require a large amount volume of water than the Pelton wheel turbine, then size of the penstock is bigger in case of Francis turbine. Basically, material we will use for the penstock pipe is generally steels. And if we talk about the spiral casing, then water from the penstock enter into the spiral casing, which completely surrounds the runner. This casing is also known as scroll casing, or you can say that This is the volute casing. Now, if we talk about the main, that is the cross-section area of this casing, decrease uniformly along the circumference to keep the fluid velocity constant in magnitude along its path and towards the guide vane. So we this is basically the spiral casing, and this is the eye of the shaft, and these are the blades. Two types of blades are there. One is guiding blade, and other is the fixed blade. So this part is called the runner, and this is the penstock pipe through which water enters into the casing. This is the guide vane. So we can say that this is so because the rate of the flow along the fluid path in the volute decreases due to the continuous entry of the fluid to the runner through the opening of the guide vanes. Material, what is the material is concerned? For low head, concrete casing with a steel plate lining is required, and for the medium head, welded rolled steel plate casing is required. And if we talk about the high head, then cast steel plate casing is required. Now the scenario is going to be changed. What is the guide vane mechanism? Then what is the guide vane mechanism? Basically, a series of airfoil shaped vanes called the guide vanes or the wicket gates are mounted on the casing. Guide vanes are fixed between the two rings in the form of wheel. However, we can swing about their x on axis, and the guide vanes are fixed between the two rings in the form of a wheel. And we can say that the basic purpose of the guide vanes is to convert a part of the pressure energy or its entrance into the kinetic energy and the direct the water or the fluid on the runner blade at an angle appropriate for the design. Guide vanes or the guide blades can move on its pivot center and hence change the area of the flow. Depending on the load fluctuations, the governing mechanism change the position of the guide blades, and hence we can say that the area of the flow show that the turbine rotates with a constant speed. So now, if we talk about the basic of this turbine is concerned, then what is the function of runner? What is runner? It is the most important component of the Francis turbine, and the runner of the Francis turbine consists of a series of curved vanes, eventually arranged along the circumference in the annual space between two plates. The runner vanes are so shaped that water enters the runner radially at the outer periphery and leaves it axially at the inner periphery. Most of the portion of the pressure energy is converted into kinetic energy as water flows through the runner. The driving force on the runner is both due to the that is impulse and the reaction. Impulse, what is impulse? Whenever a force apply on the object for a very short time, the impulse is said to be occurred, and we can say that the driving force on the runner is both due to the impulse and the reaction effect of the turbine. Now come to the what is draft tube? What is the function of draft tube? Basically, it is a pipe or the passage of gradually increasing cross-sectional area towards its outlet end, and it connects the runner exit to the tail race. As the pressure of the reaction turbine is concerned, then pressure of the reaction turbine decreases continuously as the water passes through the guide vanes and the runner. It does below atmospheric pressure at the outlet of the runner, and the draft tube is used to discharge the water to the tail race by increasing the pressure of the atmosphere. Now the draft tube must be submerged below the level of the water in the tail race. What is the material requirement? Material basically a steel plate. So this is basically the function of the draft tube. So we have a number of parts in racing turbines. So we have to know what is the function of each part and which part is responsible for which function. Now come to the working principle of the Francis turbine. So in case of Francis turbine, basically water flow through the penstock under pressure enter the spiral casing, which completely surrounds the runner. From casing, water passes through a series of guide vanes which directs the water to the runner at a proper angle. And the pressure enters, energy of the water reduces continuously as it passes over the guide vanes and moving vanes. Basically, the difference in pressure of water reduces continuously as it passes over the guide vanes and moving vanes. And the difference in the pressure at the stationary guide vanes and moving vanes is responsible for the motion of the runner vanes. And finally, water is discharged to the tail race through the draft tube. Basically, if we talk about the velocity triangle, so the velocity triangle, work done and efficiency of the turbines, how we can calculate. So basically, this figure shows the velocity triangle in case of Francis turbine. So in this case, we have this is the wheel part, and this is the inner periphery, and this is the outer periphery. So come to the previous slide. So we can say that this is the center of the wheel, and R1 and R2 are the two radius. R1 is the outer radius, and R2 is the inner radius. In this case, R1 is the outer radius, and R2 is the inner radius. So we can say that inner periphery is this is the inner periphery, and this is the outer periphery. These are the veins, and we can say that in case of velocity triangle is concerned, this is the main vein, and this is the two types of triangle it is concerned here: inlet velocity triangle and outlet velocity triangle. So this one is the inlet velocity triangle. This is the outlet velocity triangle. So we can say that there are number of parameters is concerned. So this is here we have U2 and VW2, velocity of whirl at section 2, that is VW2, and VW1 is the velocity of whirl at section 1. So we can say that this is the angle is concerned. This is the V1 absolute velocity at inlet, and V2 is the absolute velocity at outlet. VR1 relative velocity at inlet, and VR2 is the relative velocity at outlets. Similarly, we have two velocities, that is U1 and U2. That is, we can say that this is the tangential velocity at section 1 and 2 respectively. Now, we can calculate how will you find out the efficiency of these turbines and what are the other requirements. So basically, there will be a general expression for calculating the work done by the runner. So we can say that work done per second. If you want to calculate work done per second, then WD indicates the work done per second. It is the formula is M VW1 U1 plus minus VW2 U2. So first you have to know what is VW1, VW2. VW1 and VW2 are the whirl velocity at inlet and outlet, and U1 and U2 basically the tangential velocity at inlet and outlet. So this is the vein, and we have two velocity triangle, that is ABD and EFG. These are the two velocity triangles, and if we if you know the value of V1, V2 and VW1, VW2 and U1, U2, then you can calculate the work done. So this part, that is curve part EB, shows the vane or the blade of the Francis turbine. And now if we can say that work done per second, another formula is for work done per second, that is rho AV1 VW1 U1 plus minus VW2 U2. Basically, m dot represents the rho AV1. So if beta is less than 90 degree, then we can say that the positive sign we have taken the answer. If beta is greater than 90 degrees, then beta is greater than 90 degrees, then we can take negative value for the calculation. So the maximum output and the runner of the Francis turbine is so designed that there occurs a radial discharge at the outlet tip of the blades. And for the radial discharge at the outlet, we have to take beta as 90 degree and VW2 as 0 degree as shown in the figure. So we can easily calculate the work done per second with the help of the formula m dot VW1 U1 like that. And this is the basically the formula for velocity triangle, and this indicates the complete figure. And you can see that this part is known as VW1 and this is known as VU1. This is the V1 and here is the V2. Vf1 is the velocity of flow at inlet and Vf2 is the velocity of flow at outlet. And we can say that phi and alpha are the two blade angle and inlet and outlet. So if we talk about the next, what is the hydraulic efficiency is concerned. So what is hydraulic efficiency? To find out the hydraulic efficiency, hydraulic means water. Basically, hydroelectric power plants are based on the water energy, and the water strike on the bucket of the or the blades of the turbines. Then turbine rotates, turbine shaft rotates, and due to this, a hydraulic energy converted into the mechanical energy, and with the help of dyno, we can convert mechanical energy into the electrical energy. So, if you want to calculate the hydraulic efficiency, then hydraulic efficiency is denoted by eta H. H indicates for hydraulic. Now, runner power. Runner power, that is the power uh, developed at the runner, and power power developed by the water. So we can calculate with the help of the formula eta H indicates the hydraulic efficiency. This is equal to m dot Bw1 U1 divided by rho g q h, where q is the discharge and g is the acceleration due to gravity, and rho is the density and h is the head. Basically, discharge is the quantity of fluid flowing per second through any pipe or the channel. So we can say that the value of G you have to take 9.81, and density, that is if you density rho indicates the density of water, that is 10 to the power 3 kilogram per meter cube. H indicates the head of water maintained, and VW1 is basically the velocity of whirl at inlet, and U1 is nothing but only the velocity at inlet, that is tangential velocity. Now, if we simplify this formula, then rho g and rho g, that is rho q, and here is rho, so rho cancel out, and q cancel out. Then the formula for the hydraulic efficiency is little developed, that is VW1 U1 upon GH. Okay, so to calculate the hydraulic efficiency, we have to first know what is the runner power and what is the hydraulic power. Somewhere, if we talk about this velocity triangle, then you have to know how to draw this velocity triangle, and if you want to draw this velocity triangle, then you can easily solve the problem. This is basically 90 degree, angle GFE is 90 degree, and similarly angle BDA is also the 90 degree, and that is VR1. This is VR1, velocity of relative velocity at inlet, and VR2 in the figure is known as relative velocity at outlet. Similarly, VF1 and VF2 in the figure, VF1 and VF2 are known as the flow velocity. So if we talk about the basics of this turbine, then in the previous slide we have talked about the how to actually the velocity triangle is generated in the velocity, that is Francis turbine. So this is the actual figure. And if we talk about the next, what is the work done per second, then I have discussed the work done per second formula, that is m dot VW1 U1 plus minus VW2 U2. So you can calculate with the help of this formula. M dash you can change, that is UAV1. The rho is the density and A is the area, and V1 is the inlet velocity, tangential velocity at inlet. So for maximum output, the runner of the Francis turbine is so designed that there occurs a radial discharge at the outlet tip of the blade. So this type of turbine, basically a reaction turbine, and it is different from the impulse turbine. In basically Pelton wheel is the impulse turbine, and if we talk about the reaction turbine, then we can take Kaplan turbine, Francis turbine, and then propeller turbine. These are the other examples of the Francis turbines. Now this hydraulic efficiency formula is now clear, you all, that it is the ratio of the runner power to the water power. So we have to calculate runner power first, and after that you have to calculate water power. If you know the value of the runner power and water power, then you can easily calculate the hydraulic efficiency. Um, in some cases, that is the runner power that is you have to calculate first. That is m dot Pw1 U1 divided by water power. If we talk about water power, then this is rho GQH. This is the value. Now, thank you. If there any doubt, any confusion, then you can mail your query on my mail ID, that is Satyaveer Singh _GN@IIMTindia.net. Okay, and thank you. We will meet in the next lecture. Thank you.